right, so let's finish up by looking at section 3.5. Okay, we'll look at basically what we did yesterday, except now we'll have complex answers as roots. All right, so just a reminder, we've been saying this a lot. If you've got a number that's a 0 of a function, basically that means when you plug it in for x, y comes out to 0. It's an x-intercept. Right, so if a number is a 0, it's a root, it's an x-intercept. And what's one more important way to say that? If this number is a root,
Fraction.
what is a factor? What do you stick in front of that? X minus. Right? If you've got a number that's a root, you stick an x minus in front of it, and that's a factor. Okay, we've done that quite a few times. So like if I wanted you to make your own polynomial that crossed the x-axis at 2 and 5, well, if it crosses at 2, x minus 2 is a factor. If you want it to cross at 5, write that as a factor. If you graph that, it would cross the x-axis at exactly the 2 points you want, 2 and 5. Okay. If a polynomial doesn't cross the x-axis, then that means we don't have any real answers to the problem. Okay, real answers include everything you can write as a fraction and everything you can't. Okay, things you can't write as fraction, pi, square roots of numbers that are not nice, like square root of 3, square root of 7. All right, so let's take a look at this one. This is what says y equals x squared plus 1. Okay, so x squared is a parabola. And what does it do when you stick a plus 1 on the end? Yeah, it shifts it up 1. We talked about transformations back in chapter 2. So this is a parabola, which if we graph it, it never crosses the x-axis, which means there are no real answers to this problem. Okay, any question on that? Doesn't mean we can't figure out a way to make it 0 if we're willing to extend the kind of numbers we use to imaginaries. All right, so this is just a reminder of what I is. Okay, I is what we use to represent the square root of -1. Okay, this isn't something I can prove to you. I cannot prove to you why I equals the square root of -1. That would be like in geometry, me proving to you parallel lines don't cross. I can't prove that. The fact that parallel lines don't cross, that's just a basic fact that everybody agrees on. We don't ask why, and we just say, okay, parallel lines never cross, and then we can do other things with that. But you got to have a starting point, and this is our starting point. I equals the square root of -1. We don't ask questions. Okay, then from there, we can figure out other things based on that as a starting point. This one is very important to figure out, what I squared is. Yeah.
Can you go back up a little bit?
Back up. Nothing above the previous page.
Yeah, just to like the graph not touching part.
Oh, the graph not touching? Yeah. Yeah, so the graph never touches the x-axis.
But like what was the notes for it?
Just that. All right, so I want to figure out what I squared is. Okay, so in that definition, it says I is the square root of -1. So I'm just going to take that and fill it in right there. So I is the square root of -1, and I'm going to square it. Okay, that's I squared. Well, what happens when you square and square root? Yeah, they cancel out. So if that's gone, and that's gone, what am I left with? -1. That's the key. All right? Anytime we get I squared in a problem, it's equal to -1. Right? So if you see a final answer on a test that has I squared in it, that's not right. I squared can always be simplified to -1. let's try plugging that into the problem we just had. Okay, that graph. All set on the left?
Yeah.
All right. I'm just going to take I and plug it in for x. Take I. Just going to fill it in for x. Okay. What's I squared come out to? We just said that. -1 plus 1. What's -1 plus 1? We just found something we can plug in for x. And we made y come out to 0. Okay? So I is a root of this problem. It's one of the, there's two. Okay? This exponent tells us how many answers there are. So I is one of the answers to this problem if you want to find something to plug in and get 0 as the answer. Okay? But it's not real. It's imaginary. Okay. Any question on that? So I'm just showing you an example where I would work. All right. Now for kind of the next 20 or so minutes, we'll do a quick review of what complex numbers are, how you add, subtract, multiply, and divide them, and then we'll get to the pre-calculus part. Okay, that's what a complex number looks like. Okay, it's of the form a plus bi. When you write a complex number, you put the real part first, put the imaginary part second. Okay, so here's the real part, just A, and the imaginary part is just the B. The I is just there to tell me what's next to it is imaginary. Okay. So here's an example of a number with a real part of 2 and an imaginary part of 3. This first one here is 3i. Okay, that's a complex number. Okay. But it doesn't have a real part. So if all you have is an imaginary part, what do you think the real part would be? Yeah, you could pretend it's 0 if you want. Most people don't write it that way, but you could. 0 plus 3i. Real part 0, imaginary part 3. Same thing here, -7i. There's no real part. What about 4? It has a real part, but it has no imaginary part. So what's the imaginary part here?
0i.
Yeah, you could think of it this way. The real part is 4. Imaginary part is 0. We don't normally write it this way. If it's 0, we just don't write it. Right? So technically, every single number that you've studied, okay, up until now, is a complex number. We usually don't talk about this part, okay, till you get to algebra 2. We just say, oh, this part's always 0, and we don't even tell people it's there. Right? If you told a first grader that the number 4 could be written as 4 plus 0i, their head might explode. So we don't talk about it. Right? We just say it's 4. We don't even talk about imaginaries. Right? Here's one that has both real and imaginary. Yeah, even today, some people's heads might explode. All right, and then this one, here's another complex number. Real part is 2/5. Imaginary part, -1. Okay, if you just write I, okay, and you don't put anything in front of it, we could always pretend there's a 1. Okay, just like if you write X, you can always pretend there's a 1. Okay, it's same idea. Yeah.
So like if you had 2/5, why do you need to have -1i?
Well, it's a complex number. Real part 2/5, imaginary part -1.
Yeah, but why do you need that?
It just might happen in a problem where you get an imaginary.
Okay.
Yeah.
I'm just like trying to
Yeah. Okay, so I'm just showing you different examples of complex numbers. Okay, not everything we do for the rest of the year is going to have I in it. Okay, in fact, we don't use I very much at all in this class. Right, there's a few lessons where it comes up. This is one of them. But most of the time, we won't even use it. All right. So when you're doing complex arithmetic, you can think of I as a letter, kind of like if you did x plus x, that gives you 2x. Well, same idea. If you did I plus I, what would that give you? 2i. 2i, not I squared. It's 2i. All right? So you can treat I as a letter. I want you to remember, though, in math, I is not a letter. Okay? I stands for something. Okay? It stands for the square root of -1. It's kind of like saying pi is a letter. Well, true, in the Greek alphabet, pi is a letter. But in math, pi stands for a number, 3.14. Okay? Same idea. Okay, when we multiply complex numbers, we use FOIL. Some people might call it double distributive property. And what's going to come up when we FOIL? I squared. Okay? Remember, anytime you get an I squared, it's -1. Okay, so I'm just kind of summarizing some of the things we're going to do, and I'm going to show you how these work. When we get to division, we're going to use something called conjugates. Okay, that's how you divide complex numbers. And taking a square root. Okay, let's look at how that works. All right, if you've got to take a square root, okay, of a negative and x is a number. Okay, we'll do some examples with numbers in a minute. First thing I do is just rewrite what's under the square root like that. Does everyone agree that -1 times x is -x? It's the same thing. All I did was rewrite it. -1 and x. And then because I wrote it as two separate things, you can split it apart. You can take the square root of the first number and then take the square root of the second number. Now this first one we already talked about. What's the square root of -1? I. Square root of -1 is I. And then the square root of x, well, it depends what the number is. If it was square root of 4, I would make it 2. If it was square root of 7, I couldn't do anything with it. Okay, my suggestion is anytime you've got an I with a square root, put the I in front of a square root. Okay, why would this maybe be not the best idea? If I'm looking at that, what would you think I find confusing about this? Well, I know I is a number, so I wouldn't think I is a variable. That's okay. But it's kind of where you put it.
Because it'd be like taking the square root of a square root.
Yeah, I can't tell. Is this I supposed to be under the square root or not under it? Okay. Take the I, stick it in front of the square root. Now there's no question. I can clearly tell the I is not under the square root. All right. But if you had something like this, okay, the square root of 16, that actually comes out to a nice number. What is it? 4. So you don't have to write your answer as I4. You can put the I after it. There's no square root, so I'm not confused if you put the I after the number now. Okay. That's perfectly fine. So the only time I want you to put the I before is if you can't simplify the square root, like square root of 5. Can't simplify it. Okay? So we'll try a couple. All right, so kind of the bottom line here is anytime you take the square root of a negative, you put an I in front, and then just take the square root of the number. So that negative comes out as an I. Cheryl?
That's what I was going to ask about. Just
Yeah.
I. It comes out right.
All right. So square root of -4. Okay, that's going to be 2i. Okay, you can break it up. Square root of -1 times square root of 4. Square root of 4 is 2. Square root of -1 is I. I put the I after it because there's no confusion. There's no square root. Okay, how about, let's try the one below it. Square root of -9. 3i. Okay, it's just like the square root of 9 and put an I after it. Square root of -7. Yeah, all you can really do is that. 7 is a prime number. We can't break it up. Some numbers you can break up, and we need to do that. All right, so I see a negative. I'll put that out as an I. Square root of 20. How can you break up square root of 20? Yep.
4 and 5, which would be 2 squared root of 5.
Yep, I would break it up as 4. 4 times 5 is 20.
And could you break up the 4 to be square root of 2?
Not square root of 2, even simpler. Just 2. Okay, square root of 4 is just 2.
Yeah.
So we have I times 2, which how do we write that? 2I. And we've got this square root of 5 we can't do anything with. Okay? Any questions on taking a square root? Yep.
Do you put the plus and minus in your answer? Or do you leave
No, you don't. No, you don't have to do the plus minus.
Okay.
The only time you do a plus minus is if you have an equation like this, and you're canceling out something that was squared. Now, when you take the square root, you need a plus minus.
So if the question is just about the square root.
Yeah, if the question is just about a square root, they've already put the square root in. If they wanted the plus minus, they would have had to put it. Okay?
Okay.
When you put the square root in yourself, you have to put it. Make sense?
Yeah.
All right, so we'll try a couple add, subtract. We'll go through that quick. And then we'll do a little bit multiply and divide. And then we'll tie this in with what we're actually learning in pre-calc. Okay, when you add complex numbers, okay, think of it as combining like terms. You can combine real parts with real parts. And you can combine things that are imaginary with things that are imaginary. Okay? That's for adding and subtracting. You've got to combine like terms. All right, so this one says 7 minus 3i plus 4 plus 5i. Brendan, what's the real part of this first number? 7? What's the real part of this second number?
4.
And what do you get if you do 7 plus 4? 11. That's the real part of my final answer. Okay, Eric, what's the imaginary part of the first number?
Minus 3i.
Just minus 3.
Oh,
Yeah,
minus 3.
minus 3. And the second one?
Plus 5.
Plus 5. What's minus 3 plus a positive 5?
2.
2. And it's the imaginary part, so what do we put?
I.
I. That's it. Okay, it's 11 plus 2i. Any questions on adding complex numbers? Okay, let's just go right to a subtraction. Okay, be careful here with subtraction. You're not just subtracting the 6, you're also subtracting the I. Okay, it's in parentheses, so both of these get subtracted. So think of it as 4 minus 6 and negative 2 minus 1. Right, negative 2 is the imaginary part, minus 1. All right, so the first part. Cameron, what's 4 minus 6? Negative 2. And John, what's negative 2 minus 1?
It's negative 3.
Negative 3. And that's the imaginary part, so what do we put?
I.
I. All right, so think of that negative as a distributive. In fact, if you want to rewrite it as minus 6 minus I first, you can do that. But don't forget, both are subtracted. Any questions on subtraction? Can people remember this a little bit from Algebra 2? Yeah, all right, so we won't spend any more time on that. All right, multiplication. This is going to come up when we actually get to doing what we're going to do. All right, multiplication is just like doing the double distributive property. You're going to multiply all the things I just drew lines to. Okay, and there's a pattern if you have 2 and 2. Sometimes we use that word FOIL. Multiply the first, outer, inner, and then last. Okay. You're never going to have to worry about multiplying too much more than that generally. Okay, maybe we'll have 1 or 2 where we have that, but that's our pattern we use. All right, so first one, Jamie, 2 times 5 gives me 10. Right, Taryn, what's 2 times negative I? Negative 2i, yeah. Okay, and Derek, what's 3i times 5?
15i.
15i. Get some like terms. We'll worry about that in a second. And now the last part. Well, let's just start with it's a positive times a negative. Okay, Tyler, what's a positive times a negative?
Negative.
Negative. Okay, so we get negative 3i times I. We already took care of the negative.
It's gonna be 3.
What? Before you simplify it, what would you get?
You would get negative 3i squared.
Yeah, so we've got negative.
Negative 3 times negative 1.
Yeah.
Which is 3.
Did everyone see where you get the negative 3i squared from? Okay. And now this part, if you can do it in your head, that's good. We can do that in the future. Okay. I'll combine these like terms. Negative 2 plus 15. That's plus 13i. And now this, I'm going to do it in 2 steps, just so people can see it. You've got minus 3, but I squared is what number?
And then
It's a negative 1. So we've got 10 plus 13i minus 3 times negative 1. It's negative 3. Okay. And what happens here, you have minus a minus. Becomes a plus. Now you can combine 10 with plus 3. Okay. What's positive 10 plus 3? So we get 13 plus 13i. Just a coincidence. The real part and imaginary part came out the same. That usually doesn't happen. Right? So that's how you multiply. Right? So be careful with the I squared. Does anybody have any questions or need to see another one of this? This is important. All right. So the last operation before we'll see how this applies to complex roots is division. Okay, to do division, we're going to use what's called a conjugate. All right, so what's a conjugate? Well, if you had a number a minus bi, you can pretend like it's 3 minus 4i, some complex number. The conjugate is basically when you just change the sign of, okay, that's what negate means, change the sign of the imaginary part. All right, so if you had a minus bi, the conjugate is a plus bi. So 2 plus 6i, 2 minus 6i. Those are conjugates. Just change the sign of the imaginary part. Leave the real part just the way it is.
But I squared, the one we just did. We just changed the negative 3 sign.
This one?
So it's just like we have negative 3 and negative 1, so we just change them imaginary number.
Yeah, this isn't really using a conjugate here. No. I'll show you where we use a conjugate though. All right, so let's just practice, make sure we can look at a number and tell me the conjugate. 3 plus 2i.
3 minus 2i.
3 minus 2i. Okay. Now in this case, it's already negative. So it's 4 minus 5i.
4 plus 5i.
4 plus 5i. Any questions on those conjugates? Okay. How about 3i?
Negative 3?
Yep, negative 3i. Right? If you're kind of confused, just stick in the real part. It's 0. Well, if it's 0 plus 3i, the conjugate is 0 minus 3i. Okay. What about 6?
Just
6.
Just 6. Yeah. Okay, there's no imaginary part here. So think of it as 6 plus 0i. The conjugate would be 6 minus 0i. Well, whether you plus 0 or minus 0, it's still 6. Okay? Any questions on why that one doesn't change? All right. So now, the last thing we'll do is a division problem. Okay, so when we have to divide two complex numbers, the way you do it is you multiply the top and the bottom by the conjugate of what's in the bottom. Okay, and you'll see in a second why we do that. It makes something nice happen. All Right? So to divide two complex numbers, multiply the top and the bottom by the conjugate of what's in the bottom.
So 2 plus 3i.
In this case, we're going to multiply the top and the bottom by 2 plus 3i. Yep. Any questions on why it's 2 plus 3i? That's the conjugate of what's in the bottom. Okay, and really it just turns into a multiplication problem. We just have to FOIL it out. So Jill, what's 5 times 2?
10.
10. Right, how about John? 5 times 3i? 15i. Will? I times 2?
2y.
2i. All right, and the last part, if you can do it all in your head, that's fine. If not, we can do it in a couple steps. We've got I times 3i. That's 3i squared. But what's I squared? Negative 1. So what is 3i squared? Negative 3. Okay? Okay, now in the bottom, watch what happens when you multiply conjugates. Okay, what's going to happen right here? This always happens when you multiply conjugates. 2 times 2 is 4.
You don't let it.
What's 2 times 3i? 6i. What's 2 times negative 3i? Negative 6i. That's always going to happen. Plus 6i minus 6i. Okay, anytime you multiply conjugates. All right, and the last part, you have a negative times a positive. That's a negative. Negative 9, negative 9i squared. Yeah, there's a lot of negatives here, so you might want to do it in 2 steps. Or just, you can do it all in your head, that's fine. All right, so in the top, we're going to get 10 minus 3, 7. 15i plus 2i is 17i. Now, in the bottom, if we've done this right, all the i's should eventually disappear. We got 4. Now, minus 9i squared is really this. That's going to turn into a plus 9. Minus, minus. So we've got a plus 9 and a plus 4. Yep. So we can add that up. And now the only thing that's wrong with that answer is we don't have the real part and the imaginary part separate. It's one big fraction. So the way I'd like you to write it is just separate out like this. Take the real part, put that over 13. Take the imaginary part, put that over 13. You can leave the I in the top. People usually put the I in the middle, just like I have it. Don't put it in the bottom. Okay, they put it in the middle. You know, we see that when we do something like this. Y equals mx plus b. Like when we're writing something that has a fraction, y equals mx plus b, we usually put the x right in the middle. You could write it this way, but most people don't. They put the x right in front or right after it in the middle. Okay, same thing with I. Okay, any questions on division? Mm-hmm.
Why did you add it out of the 2 halves of that fraction at the very end?
Why don't I add these up?
No, well, I mean, like, why did you separate it?
Just so we have A, the real part, and B, the imaginary part. Otherwise, it's all kind of grouped together in one fraction. So if it's a multiple choice question, the answer would be listed like I have here, not like the way it's above. So it's just that small step of putting 13 over both parts.
If we left out a test like that, would you mark it wrong?
If it doesn't say to write it in standard form, no. But if it says standard form, that is standard form. Real plus imaginary separate.
So that end part with the 2 separated, that would be standard form for division?
This is the standard form for any complex number. Okay, every answer I've done today, I've written that way with you guys. All of these numbers are in standard form. Okay, that's standard form, real, imaginary. real, imaginary, real, imaginary. We've used standard form for every problem. All right, so that's kind of the review of complex numbers. So now we'll try a few problems like we did yesterday. Same types of directions. We're going to find the roots, find the zeros, except now some of the answers might come out imaginary. All right, this is just a quadratic. So if all we have is a quadratic, what formula can we use to solve it? Just use the quadratic formula. Just plug everything in and see what happens. Okay, what's A, B, and C here? A is 1, yep, B? 1, and C?
1.
It's nice to have variation. All right, so we got A, B, and C. And just fill them all in and see what happens. Negative B. Plus or minus the square root of what comes next?
1 squared, so 1.
Yep, B squared minus
4, 1.
4 times
1 times 1.
4 times A, which is 1, times what?
C.
C, which is also 1. And what do we divide by?
2. 2 times
2 times.
1.
What letter is that we really used?
A.
A. Divide by 2A. All right, so we're going to get negative 1 plus or minus the square root of, what's 4 times 1 times 1? Yep, so we get 1 minus 4. All right, what's 1 minus 4? Okay, we get negative 3. And what tells us at this point that our answers are imaginary? Yeah, square root of negative 3. How do we write the square root of negative 3?
I squared.
Those are the roots to this problem. You can't get those on a graphing calculator. Right? If they wanted it in standard form, this is not standard form. They didn't say to, that's why I didn't. But if they did, you could write it this way. Negative 1/2 plus, let's see, dividing by 2, that's root 3 over 2i. And the other answer is negative 1/2 minus root 3 over 2i. These are the two answers I've written here circled in standard form. What do you notice about these two answers? Negative 1/2 plus root 3 over 2i, negative 1/2 minus root 3 over 2i. What are they? They're conjugates. Okay, these are conjugates. And in fact, that will always happen. Anytime you solve a problem, if you get a complex answer, there has to be another one. Complex answers occur in pairs. You're never going to have one. If you have one, you have two. Right? And it's always the conjugate. So if I had a problem and I told you 2 plus I was one of the answers, okay, when you use the quadratic formula, what do you automatically know another answer is? 2 minus I. Complex answers always occur in conjugate pairs. Always. Right? And I think I write that down on the next part. Okay, so notice the roots from the last example are conjugates. Okay? So in general, if you have a root that's a plus bi, I guarantee you a minus bi is also a root or a zero. So complex roots always occur in pairs, and they are conjugates. Okay, all the theorems that we've learned before, remainder theorem, factor theorem, synthetic division, everything works just the same with complex numbers. You don't have to change anything. Okay, I'm going to show you just how synthetic division works. Okay, it's kind of a pain, so I picked a problem that's relatively short with small coefficients. couple ones. And I picked a very small complex number. Right, and I'm going to show that 1 minus 2i is a 0. Okay, I'm going to show that if you plug that in, you're going to get a remainder of 0. So let's put 1 minus 2i on the outside. And what would be my coefficients on the inside? 1.
1.
So 1, 0, 1, 10. Okay, when you start with synthetic division, it's not bad right away. Okay, you just bring down the 1. That was easy. And now we multiply 1 times 1 minus 2i. Well, think of it as a distributive property. Does that change anything?
No.
No. So it's just 1 minus 2i. Okay, still not too bad. Now we add these up. Okay, if I add 0 to 1 minus 2i, I get the same thing. Okay, now here's where it gets a little bit of a pain. We have to multiply these two things together. Okay, so we're going to have to do this twice. We're going to have to do a FOIL here, and then one more time. Okay, but the most I would ever have you do it in a problem is twice. If you had something with a high exponent, you could have to do it 6 or 7 times. It takes forever. All right, so we're just going to have to do it twice, which isn't bad, and the numbers are small. So off to the side, so I don't mess up what we're doing, I'm going to multiply 1 minus 2i times 1 minus 2i. Multiplying this times that. All right, so I get 1 times 1. I get negative 2i, and then another negative 2i. What is that? Negative 4i. Negative 2i times negative 2i. Negative 2 times negative 2. Positive 4. Negative times negative is positive. I times I. I squared. Okay. What's 4i squared? Negative 4. Right. So now that's what we're going to write in that next column. 1 take away 4. That gives me a negative 3. Take away 4i. And now add with what's above it. Well, there's nothing for i here. So the negative 4i just stays the same. What's 1 plus negative 3? Negative 2. And this is going to be the last time I FOIL, and then I'm done. What am I hoping to get right here? Well, I'm hoping to get 0 here. So what am I hoping to get right above? Negative 10. I'm hoping that this times that is negative 10. So all the i's are going to disappear somehow. All right, so we've got 1 minus 2i times negative 2 minus 4i. Okay, 1 times negative 2 gives me...
Negative 2.
Yeah, it's just negative 2. 1 times negative 4i?
Minus 4i.
Minus 4i. What's negative 2 times negative 2i?
Plus 4i.
Negative times negative is a positive. Negative 2 times 2, 4i. Okay? And the last part, negative times negative is positive. 2 times 4 is 8. And I times I? I squared. Those are gone. What's 8i squared? And what's negative 2 minus 8? Negative 10. Add them up. Remainder 0. So we just proved that that is a root of f of x. All right? So a little bit more work with synthetic division just because of that. Bless you. Because of that foiling. But it does work just the same.
So we call that rational?
No, this is complex. Rational numbers are just numbers you can write as fractions. No I for rationals.
So, like the other day, there was a problem where it was like 2x minus 1, and you couldn't use like synthetic division.
Yeah, we've talked about maybe trying to extend synthetic division if you're clever. Yeah.
Like, could you implement like
I'm sure there's a way you could kind of extend it to work, but not something we're going to have to worry about in this class. But yep, I'm sure there's a way, if you're really clever, you could figure it out.
But how we don't write it out?
How would you write it? This is it. This is all you'd write. You'd stop here. Yep. You can't factor this. Okay, the reason you can't factor this, usually we say, oh, here's our quotient. Now we could factor it. You got all these i's in it, all right? If you got i's in the quotient, we're not even going to touch that, all right? Unless we ended up with all the i's canceling out somehow, then we could factor it. But don't worry about that one here. Yep.
Can you multiply out the 1 minus 2i squared again? So like
The 1 minus 2i?
Yeah.
So you have 1 times 1. 1 times negative 2i is negative 2i. And then 1 times negative 2i is another negative 2i. So that's negative 4. So you have negative, think of it as negative 2 and another negative 2. And you're combining them. 1 times negative 2 is negative 2. 1 times negative 2 is another negative 2. So it's negative 2 minus 2, which is negative 4. It's just like, it's like doing 1 minus 2x times 1 minus 2x. 1 times negative 2x is negative 2x. 1 times negative 2x is another negative 2x. Negative 2 take away 2, negative 4x. We're just doing it with an I instead of an x. But same idea as that. Mm-hmm.
So, like, when you're doing normal synthetic division, you know how you have to, like, write out a polynomial for what you get?
Yeah.
As the answer? You
Wouldn't do that here. Nope. We can't do that here. Yep. You'd stop right here. You just say, yep, I got remainder 0, so I showed that 1 minus 2i is a root. Done.
And that's as far as it can ever go?
That's as far as we're ever going to go with that. Yep. I'm going to stop right there. All right. So some polynomials, when you graph them, I can guarantee you they will go through the x-axis. Okay. Sometimes, like a parabola, it doesn't. But how come an odd degree polynomial, I can guarantee you will go through the x-axis every time, at least once. Maybe more than once, but at least once. Yep?
Because when you cube a number, compared to squaring, you can have a negative and a positive.
Okay, so I like the way you're thinking. You're on the right track with negative and positive. What's the end behavior of anything that's odd? Like a parabola is even. It's up, up, or down, down. But what about odd? One end goes down and the other end goes up. Okay, so any odd degree polynomial, one end goes down forever, one end goes up forever. And if you're going to go down forever and up forever and never lift your pencil, do you have to go through 0 at some point? Yeah. So go down forever, go up forever. If I'm going to connect these two dots without picking up my pencil, at some point I can try to avoid going through 0, but at some point I got to cross 0. Okay? So odd degree polynomials will always have at least one real answer. Okay? That's why. All right, so let's try this one. Find all zeros of x cubed minus 1. All right, this is one that, first thing I would do is try to find a rational root. Okay, you're going to have one like this on the test. I want to find, there'll be 3 answers. How do I know that? There's an exponent of 3. Okay. And it's odd. Well, I guarantee there's going to be one real. And imaginaries come in pairs. So there'll be one real, 2 imaginary. There's your 3 answers. Okay. So let's see if we can use the rational root theorem, figure out what a rational root could be, and then divide through by synthetic division, and that'll turn into a quadratic, and then we can solve it from there. Okay. What are my factors for P?
Plus or minus 1.
And Q?
Plus or minus 1.
All right. So Using the rational root theorem, P over Q, all the possibilities are just plus or minus 1. Now, there's so few possibilities, I don't even think we need to graph it and use the table. Let's just plug it in ourselves and check it. Arithmetic's pretty easy. Let's try -1. If you plug in -1 minus 1, what's -1 cubed?
-1.
What's -1 take away one more?
-2.
-2. Is that 0?
No.
No. So -1 doesn't work. Let's try +1. What's +1 cubed?
1.
1 times 1 times 1. Just 1. Take away 1? 0. Okay. 1 is a root. Okay, if you want to put this in and use your table, you can, but I think this arithmetic's pretty straightforward. All right. So just as a reminder, if 1 is a root, what is a factor? X minus 1 is a factor. Good. Okay, so 1 is a root. Let's divide through synthetically. Put 0 for x squared, 0 for x, minus 1. Since we're dividing through by a real number, we're not going to have any i's here. Okay, it's basic synthetic division like we did yesterday.
Wait, we got 1, 0, 0, negative.
So my numerator, I have a 1,
Yeah.
0x squared,
Yep.
0x minus 1. This is all 1s and 0s. This should be really fast. Bring down my 1, multiply, add, multiply, add, multiply, add. All right, so what's my quotient here? What is this?
S squared
X squared plus x
plus 1.
plus 1. That's one factor. Okay, the other factor, we said 1 is a root. So what's the other factor? X minus 1. Okay, so we just factored this original problem. So if I asked you to factor that on the test, there you go. You just factored it. Okay. I'm asking for the roots. We've got the first root. How do we get the roots for this?
Fact.
You could try factoring. It's not going to work. So what else could you do? Quadratic formula. But look at this closely. X squared plus x plus 1.
All 1.
It's all ones. X squared plus x plus 1. I've already gone through this problem. How do you find the roots? Use your quadratic formula. There's the roots right there. So the other two roots for the problem we're doing are these right here. -1 plus or minus I root 3 over 2. Those are the other answers.
So if you wrote that, just that, would that be correct?
If you wrote what?
That right there.
Just this?
Yep.
All you need is what's in that box. Yep.
Don't you need the other one though?
That's all three, right? X equals 1.
Oh, you no, you
That's the first one, yeah.
plus or minus. I didn't see that first.
Yep. And again, to see how to do this, take a look back. Add example 4. Okay, we already went through that. That's why I picked this problem.
You want one of that?
I just want to double check the quadratic.
Yep, Cheryl, go ahead.
I just want to double check the quadratic formula finds the roots.
Yes, the quadratic formula finds the roots. Yep, Cameron?
So with your answer in the quadratic formula, if you split it into fractions, is it fine if you put the plus or minus in between them instead of breaking them off?
Yeah, you can write your answer this way. This is fine. If they ask for standard form, they'll break it off into 2.
If you put it into a form, instead of having two different equations, is it fine to have the plus minus in the middle still, or do you have to have plus and then a different equation for minus?
No, you can do it just like that.
Okay.
That's fine. Yep. Okay, any other questions on that one? All right. So let's finish up with this. All right, so notice in examples 4 through 6, the total number of answers that you get is the highest exponent. If the highest exponent is a 3, you get 3 answers. If the highest exponent is a 2, you get 2 answers. That's called the linear factorization theorem. So if you've got a polynomial and the degree is bigger than 0, and you have real coefficients, then when you factor it, or when you find the roots, you're going to have n of them. Okay? If you're finding roots, you're going to have n roots. If you're finding factors, you're going to have n factors. Okay? So in this one here, what's my highest exponent? 3. So how many roots am I going to have in this problem? 3. Okay? There's a couple cases. Is it possible I could have 3 real? Yeah, there's 2 ways I could have 3 real. There's one. 3 real, and they are all distinct. 3 separate times it crosses the axis. This is also 3 real. You might say, well, wait a minute, it's only crossing it twice. Well, this is repeated. So we get 2 answers here, it's a repeat, and 1 here. Those are all 3 real. Okay. This is our third case. Just crosses the x-axis 1 time. What does that mean? If there's 1 real, what are the other 2 answers? The other 2 must be imaginary. Okay? So these are the cases you could have. All right? Yeah?
So like an equation for one of those, for an example, would it be like x to the third minus 4x?
Like this one?
Yeah.
This would be something like, actually, this is what it is. So if you wanted to do something like this, I'm not saying this one looks exactly like that, but it would be similar. Okay? It would factor into 3 things. This particular problem is all reals. There's roots at -1, -2, and 3. Okay, and again, the roots do not need to be distinct. So here's, if you were to FOIL this out, what would your highest exponent on x be? X to the 5th. All right. Now, if you graph it, it's only going to cross the x-axis at -1 and +2. So it's only going to cross the x-axis twice. But that's because we have repeated roots. Okay? And I told you I'd tell you the proper name for that. In this particular problem, -1 is a root. It occurs twice. So we use this word. We say -1 is a root, or a 0, of multiplicity 2, okay, meaning it occurred twice. Okay, 2 is another root in this problem, and it occurs 3 times. So we'd say 2 is a root of multiplicity 3. Multiplicity just means it repeats 3 times. Yep.
Do you have to use a quadratic formula for that?
For this one?
Yeah.
No. What you'd have to do, well, what you could do is you could use synthetic division. You'd use your rational root theorem. Divide through by one of these roots, -1, -2, or 3. After you divide through by it, it's going to turn into a quadratic, and it's going to be nicely factorable. So this is a problem you don't need quadratic formula, because it factors very nice. Okay. If you get a problem that doesn't factor nicely, then you would. And as far as like something like this, you wouldn't be factoring something like this in class. This is just an example. I would never have this FOILed out and say factor it and get this as your answer. That would be a little beyond what we do.
That's what I was gonna say, like, how do you tell if you have, like, multiplicities?
Well, the only way to tell is if you can factor it by hand and then see, or you can graph it. And usually if you've got something that goes up, touches, and turns away fast, that's a repeat right there. So you can tell by looking at a picture as well. All right. So I think we'll stop with that. So any questions on that? All right. So that's the homework for tonight. Before the test tomorrow, okay, I'll go over the homework. We can also do a little bit of a review. And I'll also be after school today if anybody needs extra help.